Welcome back, everyone. So we are going to start the next session now. So today we have with us Dr. Shushmita Chatterjee, ma'am. Dr. Shushmita Chatterjee studied economics at the University of Calcutta. She did her graduation, Bachelor's of Science degree from Lady Brevon College, and her Master's of Science degree, post-graduation in economics from Presidency College, and completed both her MPhil and PhD from University of Calcutta. Thereafter, she joined IIMC for postdoctoral research. Currently, she is working as an assistant professor in the economics department at Maharaja Manindra Chandra College under University of Calcutta, and she is also a guest faculty of Department of Commerce. She is supervising PhD students in the Department of Commerce and Department of Economics, University of Calcutta. Her research interests are applied econometrics, industrial organization, gender studies, and entrepreneurship. She is the author of a large number of articles published in reputed journals of Elsevier, Emerald, Sage, Palgrave, and Springer, and 3 books and several book chapters in national and international publications. She is a reviewer of journals like Sage and Books Oxford. It is my great honor to welcome you, ma'am, and to have you with us today. Now over to you. Thank you, ma'am.
Thank you. Thank you for giving me this opportunity. I'm thankful to the organizer and Department of Psychology in Indian Statistical Institute. And good afternoon to all the participants.
Good afternoon, ma'am.
Hope I am audible to all of you. This is a post-launch session, and we are going to discuss factor analysis, exploratory and confirmatory both, and thereafter the structural equation modeling. And I think participants are from heterogeneous groups, some from economics background, psychology background, marketing background, finance background. Am I correct? Am I audible to all the participants?
Yes, ma'am.
Yes.
Yes, ma'am.
And as the session based on the applications, so do you people have the R Studio with you right now, so that you can do some hands-on the application part? Would it be possible for you? Otherwise, it may be monotonous like that. If you have R Studio with you, so please open your R Studio, and if you have your own data set, you can have that also, so that you can run on your own after knowing the basic knowledge about the factor analysis, confirmatory factor analysis, and structural equation modeling. Are you people doing that or not? Any answer?
Yes, ma'am. We have I have our studio at my laptop. Thank you so much.
Okay.
So, yeah.
So you can open the session as well. Is it visible? the screen?
Yes, ma'am.
Yes, ma'am.
Yes. So we will start with exploratory and confirmatory factor analysis in RStudio. We will start with discussing the exploratory factor analysis, then variance and covariance matrix, factor analysis model, model implied covariance matrix, path diagram. We will do one factor CFA. Then we will discuss model fit statistics, model chi-square, approximate fit indices, that is confirmatory factor index, Tucker-Lewis index, and root mean square error of approach. Now, this is the basic framework of doing factor analysis. Exploratory factor analysis, confirmatory factor analysis, and the extended version is structural equation modeling. So we will start with the factor analysis. Now, hope all of you familiar with the statistical tool factor analysis? Yes or no?
Not exactly, ma'am. If you could give an introduction, it would
Yes.
help us.
It is a particular multivariate technique. So please don't mind. It is not just judging you or like that. To make the session communicative, I am trying to gauge how much you are conversant with all these terms.
Of course, ma'am.
Yes. So factor analysis is the name given to a group of statistical techniques that can be used to analyze interrelations of a large number of variables and to explain these variables terms of their common underlying dimensions. That is factors, known as factors. Now, in more technical terms, factor analysis addresses and trying to analyze the interrelationship between large number of variables by defining a set of common underlying dimensions known as factors. So it is, in one sentence, it is a kind of data reduction. If you have several variables interrelated to each other, then we try to reduce the dimension, number of variables, and taking into a particular common dimension. Now, the component analysis, also known as principal components analysis, considers the total variance and derives factors that contain small proportion. Of unique variance, and in some instances, error variance. Specifically, the component analysis unites these ones or unities are inserted in the diagonal of the correlation matrix so that the full variance is brought into the factor matrix. Conversely, with common factor analysis, communalities are inserted in the diagonal. Communalities are nothing but similarities. Communalities are estimates of the shared or common variance among the variables. Factors resulting from common factor analysis are based only on the common variance. The common factor and component analysis models are both widely used. The selection of one model over the other is based on two criteria: the objectives of the factor analysis and the amount of prior knowledge about the variance in the variables. The component factor model is appropriate when the primary concern is about prediction or the minimum number of factors needed to account for the maximum portion of the variance represented in the original set of variables. And when prior knowledge suggests that specific and error variance represent a relatively small proportion of total variance. In contrast, when the primary objective is to identify the latent dimensions or construct represented in the original variables, and the researcher has little knowledge about the amount of specific and error variance, and therefore wishes to eliminate this variance, the common factor model is most appropriate. Common factor analysis suffers from the problem that several different factor scores can be calculated from the factor model, results in other words, there is no single unique solution as found in the component analysis. Now, we will discuss this particular multivariate tool with a simple example. No, I am presently doing a research about technology readiness in India. And the survey was Pan-India survey, and we had 16 item scale. Now, what is item? Anyone? Please let me know if you have an idea about Likert scale, and then the item. Yes.
Ma'am, questions in the questionnaire or whatever data collection tool we have used?
Yes, yes. So, questions of a particular questionnaire, those are treated as items, as well as indicators, as well as variables, observed variables. For this particular research, 5-point Likert scale has been used: strongly disagree to strongly agree. So the observed variables or items, they're all having values running from 1 to 5. Now, there are several dimensions. One is optimism about technology adoption. Thereafter, innovativeness. So we have different questions about a particular dimension. Say for optimism, the statements are like this: new technologies contribute to a better quality of life. Technology gives me more freedom of mobility. Technology gives people more control over their daily lives. Technology makes me more productive in my personal life. So all the optimistic questions are there. And for innovativeness, we have several such questions, 4 items or 4 questions. And these questions will be treated as variables or indicators. Now, the total number of observations in this particular research is 1,268. So the number is very large. Now, if you have any data with you, do you have any data with you? Participants, please respond.
No, ma'am.
Okay. So these are the syntax, what we can do in R. So first we have to, I think yesterday you have a class for basic introduction in R. Am I correct?
Yes, ma'am.
Yes. So can you see the syntax? R syntax. In PPT?
Yes, ma'am.
Yes, ma'am.
So first you have to read the data in R. So first we will use this command in R to read the data. Then there is one inbuilt function, factor in R, to do particular factor analysis. Here we have chosen factors 2, only 2. So the command is, first you call the data .fa and then factor the function for this particular data and mention the number of factors you want out of your total data set. I have simplified my data and I need only 2 factors out of 8 items. Thereafter, if we want to know the uniqueness of each variable, item, score, whatever you say, then we have to give this command to R. And thereafter, if you want the loadings, then you will give this particular command for know the loadings of the items, indicators or variables in this particular factor analysis. Now this is the result. Is it properly visible, the result?
Yes, ma'am.
Okay. Now you can see for this optimism variable 1, uniqueness is 0.56. Then the uniqueness is 0.52, 0.79, and for optimism 4 is also 0.79. And for innovativeness, variable 1, 2, 3, and 4, all are having uniqueness above 0.5. Thereafter, if you go to the loadings section, you can see the loadings of each items. For factor 1, optimism, the loading is 0.726, thereafter 0.681, 0.432, 0.449, and for factor 2, variables are having loading above 0.5. what is loadings? What does it mean? Just the simple, we can say the simple correlation between the factor and the observed indicator. Nothing else. So you don't have to complicate things. It is very simple that loadings are nothing but the correlation between factor and the observed variable or item. Now, before we interpret the results of the factor analysis, we have to recall the basic idea of factor analysis. Factor analysis creates linear combinations of factors to abstract the variable's underlying communality. To the extent that the variables have an underlying communality, fewer factors capture most of the variance in the data set. This allows us to aggregate a large number of observable variables in a model to represent an underlying concept. Factors are nothing but underlying concepts known as latent variable, latent, unobserved, underlying. So we have to capture underlying concept from observed indicators, So when communality is high, then we need few factors. The variability in our data, say capital X, is given by this capital sigma, and its estimate by capital sigma hat is composed of the variability explained by the factors. Factors explained by a linear combination of the factors and of the variability, which cannot be explained by a linear combination of the factors. So one is the communality. The total variability can be segregated, can be decomposed. So one explained by the factors and one not explained by a linear combination of the factors. So that part which is explained is known as communality, and which is not explained known as uniqueness. So one is explained part and the other one is uniqueness, which is not explained. So uniqueness must be less and communality must be more. So if value of uniqueness is more, then that is not good for factor analysis. The uniqueness sometimes referred to as noise because it is unexplained. The uniqueness, sometimes referred to as noise, corresponds to the proportion of variability which cannot be explained by a linear combination of the factors. High uniqueness for a variable indicates that the factors do not account well for its variance. Now, loadings. What about factor loadings? Which range from -1 to 1. And if it is going toward 1, then that will be better. By squaring the loading, we compute the fraction of the variable's total variance explained by the factor. So communality should be high, uniqueness should be less. Up to this, is there any question? These are the just basic of factor analysis. Is there any question? I think no. So again, we will move to our codes. So we can plot the factors in R by giving all these commands. We have to plot the factors with Varimax rotation. So after doing the Varimax rotation, this is the diagram we will get in our studio session. So you can see it is very clear that OPT, that is optimism items, are here, and the variance between them very less, and innovativeness items are all joined here in factor 2 through Varimax rotation. Up to this, is there any question? No? So we are moving to confirmatory factor analysis and to structural regression model. For confirmatory factor analysis and for structural equation modeling, we need installation of packages foreign and packages Lavan. And then you have to also download library foreign and library Lavan. So this is the mathematical model. This is the mathematical model. This is just simple regression model. The first one, y equals to b0 plus b1x plus epsilon. This is nothing but a simple regression model. Y regressed on x. b0 is the intercept. b1 is the regression coefficient showing the relationship between y and x. And for confirmatory factor analysis, we are just having a simple, again, that kind of simple regression model. But this eta, lambda 1, y1 is there, which is observed. This eta term, this is nothing but a latent variable. So the difference is nothing but here we are incorporating a particular latent variable into the system. So if you have 3 items, a very simple structure, only 3 items in your analysis, then this will be the whole model for you. 3 items, y1, y2, y3, 3 intercepts, and 3 loadings are there, lambda 1, lambda 2, lambda 3, and 3 error terms. So for each item, you have particular regression equation. Now, so here we have to also calculate the model implied covariance matrix, the interrelationship between variables. Now, these are the legions for doing the analysis, the path analysis. Latent variables or the factors can be shown by this circle, observed factors by this particular rectangle, intercept by triangle, paths by arrow, and variance and covariance by this double arrow curve. So this is the particular diagram for a model with 3 items. 1 latent variable is there and 3 observed factors are there. 1 intercept is there. So nothing to worry about all these notations. This is a particular diagram just showing the relationship between a particular latent variable and 3 observed indicators. 3 observed indicators. Now, if we go back to the model, we can see this particular observed indicator y1, which is derived from this particular latent eta1. You must be very careful while writing the equations. Latent is not in the left hand side. Latent will be on the right hand side. It is exogenous. The latent is exogenous and the observed is endogenous. So when you are drawing the diagram, be careful. The arrow is going from the latent toward the observed, and the error is also going toward the observed. Latent is going toward the observed and the error is also going toward the observed. Now we can do the 1 factor CFA. You can have several indicators and observed indicators and 1 latent factor. Now, this is the basic equation for the analysis. To start with, we can have the covariance structure between different indicators. Covariance structure for different indicators. This is for 4 indicators and this is for 3 indicators. Now we will discuss the results. Again, I am questioning you. Are you people doing any kind of hands-on? If you have any data with you, then you can do the hands-on also. Are you people doing that or not? I think I am not bothering you by asking such a question. Okay. So now we have to find out degrees of freedom. Now we have to calculate the known values. How? It is by the formula P plus 1 by 2. For 3 items, you know here P is equal to 3 for 3 items. Now, fixed parameters predetermined to have a specific value. So number of free parameters is equal to number of unique parameters minus number of fixed parameters. Now degrees of freedom is equal to number of known values minus number of free parameters. Number of known values you have already calculated according to your number of items minus number of free parameters. If DF, degrees of freedom, negative, known less than free, then under the model is under identified and you cannot run the model. If it is 0, then the model is just identified or saturated. If positive and greater than free, then it is over identified and the model fit can be assessed. So we will work with over identified model. So this is the structure for 3-item CFA. This is the structure for 3-item CFA. Now, in R, we will go by the marker method. And in marker method, the first loading of each factor is set to 1. The first loading of each factor set to 1. These are the Lavan syntax. For predict regression, we need this tilde. Indicator factor analysis, we will use this equal to and tilde. For covariance, double tilde. For intercept, tilde 1. For fixed parameter, 1 star. For free parameters, NA star. And parameter A, for A star labels the parameter A model constraints. Now we can run different models for confirmatory factor analysis. Confirmatory factor analysis. Now model 1, I have run this model particular where the optimism, this is a particular latent coming up from optimism 1, 2, and 3. This is one factor 3 items confirmatory factor analysis, and I have to set the data and then summary of 1 factor 3 items factor analysis. And the R will, these are just basic syntax. You just put this syntax in R, and R will give you the result for confirmatory factor analysis with 3 items. Now, this is the result. Number of observations, 1, 2, 6, 7. And estimates, you can see the first loading is 1, as we have done this in marker method. And thereafter, for optimism 2, it is 0.833. For optimism 3, it is 0.513. So loadings are more than 0.5. Now, we can do several other models as well. And we can specify the intercept. We can specify the variance standard. Here, this is the variance standard method. And this is the result. So here the factor loading is not 1 for optimism 1. Now we will go to model fit statistics. Again, I am asking you, is there any question? Okay. So for model fit statistics, we will discuss model chi-square, then approximate fit indices, comparative, Tuckle-Lewis, and root mean square of error approximation. Now, here the hypothesis is the estimated model is equal to the population model. The estimated variance covariance matrix symbolized by capital sigma theta is equal to the population variance covariance matrix. Usually we try to reject null hypothesis in our regression analysis, but here if we accept the null hypothesis, that will be better. So there is estimation of variance covariance matrix, and there is a particular population matrix. With this particular equation we need, and we don't want to reject this. And this capital S is the sample variance covariance matrix. Sample variance covariance matrix. Now, there are several measures of fit in CFA. Absolute approximate fit index, absolute and incremental, and model chi-square. These are the formulae for root mean square error approximation. If RMCA is less than 0.05, then you can say the model is a good fit model or close fit model. 0.05 to 0.08, reasonable approximate fit. And if it is greater than 0.1, then we can say it is a poor fit model. Now, for CA5, values can range between 0 and 1. TLI, again, that is Taka-Lewis index, between 0 and 1. So closer to 1, it is a good fit model. And for RMCA, it must be less than or equal to 0.05. Now we can have fit statistics as well in particular R programming, and the command is we have to give the command summary about the CFA we have done, and we will get this result. Now we can do two-factor confirmatory analysis as well with correlated factors and without correlated factors. So if the factors are correlated, then the path diagram will be like this, where the factors, latent variables or latent factors, here shown as eta 1 and eta 2, correlated to each other, and these are all indicators. All rectangles are indicators, and the errors are given to all indicators. So we can run correlated to factor by marker method, where we can run another model. Say here it is M4B, the model name. This optimism latent indicator, here we have taken 4 observed indicators, optimism 1, 2, optimism 4, and for innovativeness also 4 indicators, innovativeness 1, 2, 4. And we can run the model, and when we can get the summary of the results. And for uncorrelated, here you can see these two are correlated, and for uncorrelated we have to write this. I have highlighted. If it is uncorrelated, then you have to give the command 0 star before one factor to show that these two factors are uncorrelated. Now we can fit the model. I have named this as TRI, Technology Readiness Index fit model, with 2 factors, and we get the results. As we have used the marker method, this is the estimation results, where you can see in innovativeness latent, these values are more than 1, but you don't have to worry. You can get such result. Now we can plot this particular result by installing package same plot and then plot the result, and you will get the diagram like this. This is inbuilt R diagram. inbuilt art diagram showing the all paths, the covariance between optimism and innovativeness as well, and also the loadings for different factors. We can have the fit measures as well. We can have the fit measures as well. CFI, RMCA. These two are very necessary fit measures and usually used in research papers. And for this particular analysis, it is CFI, comparative fit index, is 0.956. And the root mean square error approximation is 0.053. So these two are very, for CFI, it is very close to 1. So the measure is good measure and the model is a good fit model. And from RMCA value, we can say as it is just 0.053, that is, we can say it is equal to 0.05 and it is also a very good fit model. So up to this, I have discussed exploratory and confirmatory factor analysis, their model and the fit indices. So do we have any question? Do we have any question? Then I will take 9 to 10 minutes interval or intermission. Then thereafter we will start structural equation modeling and session with RStudio.
Okay, thank you, Dr. Sushmita Chatterjee. I think the basic concept for understanding the structural equation modeling, you have nicely covered. The students, they have understood your instruction, your explanation. I hope so. So now it will be at least 10 minutes rest. After that, Dr. Chatterjee will start the next program. Thank you, Dr. Chatterjee.